Okay, so I'm very pleased to be introducing our speaker, our first speaker for the winter session. And he's a person that really needs no introduction. And I thought I would just do a quick quiz of show of hands of who has taken the beekeeping course from Dr. Currie. Well, that's pretty good, very good. And who else has heard him talk before? Oh, that's good. So, I guess there's a few of you that don't know who he is, so I'll continue with my introduction. Dr. Currie is a former professor and department head in the Department of Entomology at the University of Manitoba. He had taught a wide range of courses in the diploma, degree, and graduate programs in the Faculty of Agricultural and Food Sciences. His research interests focused on issues related to the biology and management of bees, and really honeybees, leaf-cutting bees, and native pollinators, and on the crops they pollinated. A major focus of his research relates to how parasites and disease and other stressors such as nutrition interact to affect winter survival of bees. He listed all the courses he taught, and it was a long list. I will skip that. It's in the newsletter. He retired from the University of Manitoba in December of 2023 and has been appointed Professor Emeritus, where he is continuing some teaching in things he loves, such as beekeeping and research. Please join me in welcoming Dr. Currie.
Thank you very much for inviting me to come to the meeting tonight. It's kind of a pleasure to be able to talk to you all and kind of do it at a time of year when I think there's a lot of relevance to the type of topic that I'm going to be speaking about tonight. A lot of the work that has been done on sort of understanding the development of winter bees was pioneered by Lloyd Harris, who's sitting in the audience there, and I was just mentioning to him that I was kind of scanning the website here, and almost every talk that's been given on the Red River Apis website seems to include some data that was derived from his master's thesis many years ago. And if you follow people like Randy Oliver, or Lloyd Harris, Gard Otis, or Heather Matilla, they've all used Lloyd's data, and it's just been a wonderful source of information that's kind of benefited beekeepers across North America in terms of understanding what's going on in the development of populations going through winter. So I'll be highlighting a bit of that data tonight and also talking about some of the studies we've done using Lloyd's data, partly as a way of explaining how some of our results can be impacted by the development of bees going into winter. There's been a really long history of understanding how to winter bees in Canada. Obviously, bees aren't native to North America, so we kind of had to figure out how to winter them. They got established down in the US, and they can do quite well down there with the milder climates. But up in Canada, back in the good old days, we used to import a lot of bees from the southern US in packages and things like that as a way of renewing our stock. And people used to winter first, usually in cellars, and would kind of get the bees through winter in that way. There was a lot of work done at Brandon at developing mechanisms of wrapping colonies and things like that that we still use today for those of us who winter outdoors. The trick in getting bees to successfully get through winter is to really pay attention to details. And you have to pay attention to details not just going into the fall at this time of year, but as you'll see, almost throughout the entire beekeeping season. You really have to stay on top of the management, especially today when there are so many stressors that are affecting bees. Obviously, Varroa is the number one stressor, but there are a host of other pathogens and stressors, nutrition and pesticides that affect our bees, and those kind of all interact to cause problems. So essentially, if we want to get our bees through winter with a high degree of success, we kind of have to tick all the boxes and make sure we're watching all those potential things. So honeybees are, as you all know, social insects. They like to nest in their natural habitat in a cavity, in a tree, usually in a hollowed out tree. This is a photo here from Mark Winston's book, The Biology of the Honeybee. And it depicts a tree here on the left with some comb that's built by the bees inside the tree. And this soccer ball-like structure that you see in there represents the wintering cluster. The cluster is sort of in a cool condition, when it's say -10 on the outside, going to have a kind of an outer ridge of bees that is fairly densely packed. And those bees are going to be quite cool in temperature, anywhere between about 5 to about 10 degrees Celsius on the outside of that mantle, or the outside of that crust of this cluster. As you get into the inside, the bees get a little bit more loosely structured, and essentially when you get in the very, very center, if there's some brooding going on, it can be as hot as 34 degrees Celsius, even though it's very, very cold outside. There's a lot of convection and evaporation going on in here, as there would be in a normal colony or in an inside wintering building, where the bees are consuming the honey all winter long. They're converting that honey into energy that creates heat, and they use that heat to warm themselves and warm the cluster. They don't really actively warm the entire cavity, but they will warm the inside of the cluster. Bees that are on the outside of the cluster eventually get cool, move to the inside, and there's kind of a continual rotation of bees from the inside to the outside throughout the winter. The cluster is quite dynamic as it goes through winter. This is just a slide from the book, The Hive and the Honeybee, a chapter that Martha Spivak and I wrote, along with Currie-Preparing. And it just depicts a cluster in December, where you've got that fairly tight cluster, really cold conditions outside. Outer edge of that cluster might be around 7 degrees Celsius. As you move into the center of the orange dot there, possibly around 24 degrees Celsius. And that would be the type of scenario that you would have when there's no brood rearing going on. The second depicts the same cluster in March. It's now spread out. It's more loosely clustered. There's a kind of a hot area in the middle where there's some brood rearing going on, around 30 degrees, 33 degrees Celsius. So you can see that the cluster can shrink and expand depending on needs, depending on ambient temperatures, and depending on the activities going on within the colony. There is brood rearing that goes on during winter. Lloyd Harris did some work on that. Some the students in my lab, like Paul Kozak, have done some work on that. And the bees need the flexibility to be able to sort of adjust their cluster dynamics in a kind of flexible way. They also need to be able to adjust their physiology, so that if there's brood rearing going on in the winter, they have to be able to supply that brood with the nutrition it needs, so they need to be physiologically flexible as well. But the bees that are found in the winter cluster are not the same generally physiologically, from a standpoint of physiology, as the bees that we have in summer. There is a whole host of activities that a colony will go through, and it has this age polyethism, we call it. It's an age-based division of labor. Bees, when they're first emerging from their cells, do activities inside the hive. They're associated with cell cleaning, capping the brood, tending the brood, feeding the brood. Those are what we would call nurse bees. When they get a little bit older, they attend the queen, do some more sophisticated tasks like receiving nectar from other bees, cleaning debris from the hive, packing pollen, building comb. And in their oldest sort of state, they get into tasks that are outside the hive, like ventilating, guarding, and foraging. And these tasks like foraging are the riskiest behaviors, and essentially when a bee starts flying, a bee starts dying. As soon as they start getting out there and foraging for nectar and pollen, it's like the number of miles on a car. Once you hit 100,000 miles on your car is probably not going to last that long. Bees are very similar in that respect. Once they start putting a lot of miles on the clock, they just wear themselves out. They're also more exposed to risk from predation, other things. Wind events, rain events can sort of take them out. Now, if you look at the scale here, it's kind of interesting because we have age of first foraging maybe as early as about 10 days of age after it emerges from the cell. There are documented cases where it's been a little bit earlier than that. Usually around 20 is when they start first foraging, and they're mostly done if they're really active in a really hot time during the summer, around 30, and that extends out to about 40 days. Now, what is interesting about this scale is that it goes from 0 to 50 days. So if you've spent any time in the province of Manitoba, you're probably wondering if a bee's not going to last any longer than 50 days, how's it ever going to survive our winter? Well, this particular scale is not including that cohort or behavioral kind of function of bees that are going into winter and becoming what we would call winter bees. And the winter bees can live much, much longer. There's a number of glands and things I'm going to be talking about during the course of this presentation, and I'll just go through a few of them. This is just a depiction of kind of an inside look at a honeybee worker. It's a diagram that's taken from Dade, The Anatomy of the Honeybee, I think is the title of the book. Classic book, really nice illustrations. And it shows some of the glands and things that are found within the honeybee's kind of body that are somewhat relevant. Up here at the top, we have the hypopharyngeal gland. The hypopharyngeal gland is depicted here as a long, drawn-out string. It actually is masked right in the front cheeks of the bee. It's kind of like a long, pearly string of pearls if you pull it out during your dissection, and it can vary in size from being nice, plump kind of pearls that are in the state where they're ready to secrete lots of glandular food that the bees will feed to the larvae, or it can be more kind of withered and non-functional. And it's very, very important in both nurse bees and in wintering bees. There is a gland here. This isn't a picture of the gland. This is an ocelli, but right about this location of the head, there's if you kind of peeled away the top layer of the head, there's a couple of structures that are called the corpora lata, and they're like a little tiny golf ball, and those secrete a hormone called juvenile hormone. Now, juvenile hormone is thought to be quite important in regulating a number of functions in the honeybee that's very closely tied to division of labor, and it also seems to be important in regulating some of the processes that go on in wintering bees. The juvenile hormone is basically secreted, and it goes into the hemolymph of the bee. The blood of the bee is kind of just circulating throughout the entire body. It's like a big sac, and the blood just circulates around in the sac. And that hormone, juvenile hormone, can act on a number of things, but one of the targets of that particular hormone is to interact with the fat body. And when it interacts with the fat body, it can stimulate the production of vitellogenin and other blood proteins and lipids. And then it's vitellogenin and many of these blood proteins and lipids that really kind of build up to very high levels in wintering bees and give them the ability to survive with a very long lifespan, that in combination with the fact that they're not flying and dying. So if you look at physiology of nurse worker and forager bees, this is data from a researcher called Doak. And if you look at nurse bees over here on the left panel, the head is represented here with these little gray spots being the hypopharyngeal glands. This sort of squiggly line here is a chemical formulation of the juvenile hormone. This is representing a gel that indicates the hemolymph proteins. And this is a sort of a depiction of what a molecule of vitellogenin would look like. The size of the dots here is representative of the relative amount of each of those compounds. So in a nurse bee that's busy tending brood, using those hypopharyngeal gland secretions to feed the other bees, the hypopharyngeal glands are well developed. The total hemolymph proteins is pretty high because it's got to feed the hypopharyngeal glands. Vitellogenin is fairly high, has to feed the hypopharyngeal glands, and juvenile hormone is relatively low. When you get into a foraging bee, the amount of juvenile hormone, relatively speaking, increases, and as that juvenile hormone increases, it stimulates the bees to become foragers. Simultaneously, it also suppresses the production of vitellogenin, tends to suppress the hemolymph proteins and the hypopharyngeal glands. You can take a bee that is just born, treat it with juvenile hormone, and it will become what we call a precocious forager, so it will basically start foraging much earlier in life than it normally would. So in a foraging bee, low vitellogenin, high juvenile hormone, low hypopharyngeal glands. In bees that are kind of ramped up for winter, the ones that we would refer to as winter bees, we have a lowering of juvenile hormone, so very low levels of juvenile hormone, really high levels of vitellogenin, that lipoprotein that is used as a storage protein that promotes longevity in bees, and really high levels of the hemolymph proteins, and high levels of activity in the hypopharyngeal glands. So what we want to do when we're preparing bees for winter is really encourage and support the development of these winter bees. So when does that happen? This is where Lloyd Harris's study comes in. Fantastic work that he did, getting up really early in the morning, marking tons of bees, taking photographs, going back every 12 days. And so these sort of bubble charts indicate the development of winter bees throughout time. So we've got on the bottom axis 31 August, 12 September, 24 September, 6 October, going all the way to 5 December. And the point Lloyd always tries to stress is that if you've got bees that are around on the last day of August, they're pretty much all going to die before you get into winter. So it's not until you get into these cohorts here, the yellow one and the orange one, that they start moving along, and those are going to be forming the bees that become your winter bees. So your winter bees are all being produced mostly in September, and not really much happening in August. So when you see a population graph like this, the lines on the bottom here show the amount of sealed brood in the hive. That translates into a worker population that peaks somewhere around 40 to 60,000 workers in the middle of the summer. And then as the amount of brood, as the amount of forage available tapers off, as conditions get a little cooler in the fall, the workers start to die off, and the brood level starts to decline. And it's on this graph here, you can see these blue dots that I believe Lloyd put on this graph. And so many people have redrawn his graphs, I'm never sure who's, but I'm pretty sure this is Lloyd's. So these are the ones that are the August ones. They're going to be dying before winter, and these ones here, the yellow and the orange and the green and so on, are going to become the ones that form your wintering population. So they're on this graph, those bees that form the wintering population. Now you'll see that the bees, when they go into winter, they could have anywhere from 20,000 to about 10,000 bees going into winter. When they come out of winter, those initial bees that come out of winter are going to die off, and then the queen is eventually going to start producing brood. And when that brood starts to kick in, that worker population is going to start that logistic growth phase. So what we want to do when we're preparing bees for winter is make sure that we're not doing anything to mess up this period when these sensitive bees are being produced. And this is, I believe, in Lloyd's graphs, depicts the actual time when the sealed brood is there. So you have to remember that the eggs are produced much earlier than that, like 21 days earlier than the emergence of those bees. So we did one experiment that was basically designed to try and look at what happens way in advance of preparing bees for winter. This isn't the type of study that Lloyd did where he marked bees. We did a similar study to that I'm going to show you in a few minutes. But essentially in this study, we were trying to look at the effects of Varroa and some of the viruses that the bees harbor, and how your treatment regime throughout the season can affect the survival of those colonies over winter, which is directly affected obviously by the production of those winter bees. So we set up an experiment where we're trying to essentially uncouple the effects of the virus from the effects of Varroa, and essentially develop treatments where we would have some that would be high Varroa with low virus, high virus with low varroa, and medium virus with medium varroa. So we used Apivar. We had a control that had no treatments. We had a group that was treated only in spring over a period of a couple of years. We had a treatment that was treated each fall, and then we had a treatment that was spring and fall. And we predicted from this that if we kind of created this kind of treatment, this is what we would expect to see in terms of the response of varroa. In the control group, the varroa would just keep growing and growing and growing and reach very high levels by the end of that second year. In the second treatment group, we expected essentially the varroa to start growing, get knocked back, start growing. And based on previous research we've done, we kind of figured that we should end up with a treatment that had moderate varroa, but because the varroa was never allowed to get really crazy high, we anticipated that that would result in relatively low levels of virus. In our kind of next treatment, we kind of had a knockdown right away, let them build up a little bit, knockdown right again. So again, low varroa with moderate virus, and then the final one where we whack, whack, whack every time, whack-a-mole, hitting the lights down every time they came up. That one we expected to have low varroa and low virus. And so we followed these over a very long period of time, going from the fall of 2014 to the spring of 2016. And the results came out pretty close to what our prediction was. When you look at the varroa levels, which are on the top, you can see the control had very high levels of varroa, over 35% infestation by the time we hit the end. The spring-treated bees had infestations of about 17%, whereas these groups that were treated in the fall, or spring or fall, both had different levels, or fairly low levels of varroa, but they had fluctuated in different ways over time. When we looked at one of the most critical viruses, which is deformed wing virus, this is a virus that you sometimes see bees with deformed wings. It's a virus that's transmitted by varroa. It's well documented that it causes problems with longevity of bees on its own. We've done some of that work in our lab. We found that, as expected, the group that had the really high varroa with high virus, where there were no acaricides applied, had very high levels of DWV. The ones that had relatively high varroa but low virus had low virus, as we anticipated. The ones that had low virus, low varroa with high virus had moderate levels of virus, so pretty close to our prediction. And then finally, low varroa, low virus, whack-a-mole treatment worked quite effectively at suppressing both varroa and virus. I'm not going to show all the results from this study, but the take-home message is that it makes a huge difference in terms of not just the varroa and what's happening with the varroa, but the interaction that's happening with the viruses over time. This is showing the mean number of workers as evaluated in the spring at the end of the experiment. And you can see that clearly the treatment that was best was the low varroa, low virus. It had the highest levels of population and the smallest amount of variability in the population. The two intermediate treatments that had either low varroa and high virus or high varroa and low virus had moderate populations coming through winter, but really high variability. So they weren't statistically any different than the whack-a-mole treatment, but they had much higher variability. So these were way more consistent in terms of the population. These had some big ones and some really crappy ones. And as you might expect, the high varroa, high virus treatments did not do very well. And the other thing to note also is that the number of colonies surviving was higher in the control than in the high varroa, high virus treatment. There were 7 that ended up at the end of the experiment in the low varroa, low virus treatment, whereas only 2 survived in the high varroa, high virus. So it really makes a difference to pay attention not only to the varroa, but to think about what virus levels might have been. So if you missed your spring treatment, and you let your varroa get out of control, you got really high levels in the spring, then you knocked it back, you may be still having some residual effects from that carryover deformed wing virus. So you might go into your colonies, you say, okay, I've got really low varroa, I shouldn't have any problems, but you're kind of getting bit by that carryover virus that's still in your bees from the season before. So the take home there is you really need to start thinking about your winter management the previous spring and make sure you're staying on top of your varroa control and your management of other stressors throughout the year. It's not just right now I'm going to treat and everything's going to be okay. I have some colonies at the lake that I did a shake on, and I shook them in the spring and they were fine, I thought, and I just shook them today, and I'm heading back out to lake tomorrow to throw something at them because they've got crazy high levels. So it's easy to get caught. Varroa can really take off on you very quickly. So control varroa early, control it to prevent damage from virus later on. The second sort of example I have relates to something that is very similar to what Lloyd Harris did. It's kind of a marked bee study where we were trying to look at the effect of different timings of treatments on the buildup of those different cohorts of winter bees. So this was done by my student at the time, Graham Parsons, who's now one of the people working in apiculture in Saskatchewan. And for his master's thesis, we had 3 different treatments that were applied at 3 different times of year. So we had Apivar, which was applied in early fall, mid-fall, and late fall. We had, at the time, the formic acid formulation was the Mite Away Quick Strips. Those were applied early, mid, and late fall. And finally, we had Oxalic acid drizzle, which was applied early, mid, and late fall. And we had a non-treatment control. And then what Graham did is he followed Lloyd's protocol, which is wacky, hard work, where you go in every 12 days and you mark all the emerging bees that was in each of these colonies. They're all given a different color mark, and then you try to follow how many of those end up into the wintering population and figure out what impacts there were on the development of those populations. I'm not going to go through this study in great detail, but I'll just give you a few of the highlights. One is that if you looked at brood area, the one treatment that you might not be surprised had an impact on brood area was the Mite Away Quick Strips, and this is just data from the treatment 1 date, which was on the 12th of September, and the treatment 2 date, which was on the 4th of October. And you can see that this is the control, this is the Apivar treatment, this is the max treatment, this is oxalic acid treatment. You can see that the formic acid really whacked back the sealed brood area at that particular time. And it happened in the first 2 treatment dates, but not the 3rd. So in this case, the impact wasn't so much on the bees that were emerging, but it was taking out the brood that would become the bees later on. One of the really interesting ones and kind of weird ones was Apivar. And these colonies we had inoculated with mites. I think I forgot to mention that. So we had very high levels of mites going into the winter. And in that situation where you had very high levels of mites going into winter, you would think getting early Apivar in would be the best treatment. But in this particular experiment, it was not. And what these different lines here indicate different cohorts that were marked on August 20th, September 1st, September 12th, September 23rd, and October 4th. And the axis along the bottom here goes from July 22nd all the way through to the next May 22nd. So these are like survival curves of the various cohorts. And you can see the control on the right here is way shifted to the right. So those bees are doing much better than these ones that are here that are shifted to the left that got the early Apivar treatment. So that early Apivar treatment, despite controlling the mites quite effectively, the interaction of the mites with that early Apivar treatment was harming that that cohort of bees, or those cohorts of bees that were being produced during the winter during that time. And so what Graham did was he created these stacked bar charts that indicate the populations of bees that were the total population of bees, but each one of these bars indicates a different cohort. And some of these had positive effects on the bees, and some of them had negative effects. For the apivar treatment, the first two cohorts were hurt a little bit by the application of the apivar. You didn't get as many bees as in the control going into winter. For the max, the first and second treatments got knocked back in a couple of these cohorts due to the sort of brood burn effect. And in the oxalic one, which was very weird, there seemed to be a positive effect of the early oxalic treatments. I'm not 100% convinced that that is going to happen every year. We tried to repeat that with a study that Sharu Sharma did in my lab recently. She's just writing up her master's right now. And I don't think that that's something you can take to the bank, but it is something that seemed to happen in 1 year. There seemed to be a positive effect of the oxalic acid in helping these wintering populations form. We kind of had a lot of theories as to why, because it didn't seem to knock back the mites at all. We didn't see significant mite drop on the sticky boards. We didn't see a real reduction in the numbers of mites on bees. So we kind of were working around a hypothesis that maybe it was either acting as an anti-feedant, preventing the varroa from feeding on the developing bees, or maybe it was having a direct effect on suppressing the viruses. But we haven't, I would say, not having seen her final thesis, I wouldn't say we've been able to conclusively prove either of those two wonderful hypotheses that I came up with. So if anybody has any other ideas, I'd be happy to hear them. And this is what the populations looked like, coming out. So with high levels of mites going into the fall, now if you apply apivar, and there's super low levels of mites, we've done that going into the fall, apivar is a successful treatment. But this was going in with high levels of mites and going in there. So I want to make that clear. I'm not saying don't apply apivar in the fall or you'll get a bad result. It's when we applied it with high levels of mites and there was some sort of interaction going on, those bees did not survive at all. The ones that did the best got a late apivar treatment. We've also been trying to repeat this and see if it holds true. The max, the early treatment, despite causing some brood burn and reducing some some of the developing population, was best as the early treatment. And then the oxalic acid, again, in this we only did one application. We didn't get really good control out of any of our oxalic acid applications. The best treatment was that early oxalic, which also led us to believe that maybe the best combination would be to do early oxalic with late apivar, which is something else we've tried, and I haven't got a conclusive result for you on that yet. The third thing that I wanted to talk about, just as an example of how to not mess up your wintering bee population, is one related to the food stores. And Brad was talking at the beginning about how he got the message about sucrose, feed sucrose. Certainly any high quality feed is good for your bees. And I think the key is to make sure that you're providing your bees with high quality feed. If you're feeding corn syrup, there's nothing wrong with that, as long as it's high quality corn syrup. If you're feeding sucrose, there's nothing wrong with that as long as it's high quality sucrose. You do have to be careful with things like canola honey that granulate in the winter and can cause problems with dysentery and other things, and maybe harm your wintering success. So you want to feed lots of food, and there's lots of studies that have correlated both cluster size and colony weight going into fall as being predictors of good wintering success. So you want essentially nice heavy colonies going into winter so the bees don't eat themselves out of house and home. And you want larger cluster sizes that are more resilient to the sort of changes in weather we're seeing nowadays. But I'm not going to talk about those today. I'm just going to talk about the feed quality and some work that we've done recently on sucrose. So I'm not going to talk about the corn syrup stuff and all that. But essentially, when you feed anything that causes stress on your bees, it often causes dysentery. That dysentery can be caused, in the old days we used to say, by nosema. The form of nosema called nosema apis would often be associated with bees defecating on the outside of the hive, like you see here. This is all defecation by bees. The new form of nosema, which is nosema cerani, is said to be a dry nosema and isn't as tightly correlated with signs of dysentery. So it's not kind of a it's nosema if you see this, for sure. It's probably not. You can take scrapings from the poop and look for spores, and usually when we see this nowadays, we're not seeing nosema spores in the poop. It can be caused by pesticides. We did a study with some work we were doing with Genome Canada where we were trying treatments that had apivar and those that didn't. They had relatively low levels of varroa. I think they were like 1 or 2% in the fall, and we put apivar in some and apivar not in the others. And the ones that had apivar came out with significantly more dysentery than the ones that didn't. But it didn't harm the bees. The cluster scores and everything else, the colony weights were okay. So the bees were just experiencing stress, exhibiting signs of stress, but they weren't actually economically harmed by the apivar. The other thing that is often associated with it is poor feed, and poor feed can come in the form of canola if it granulates inside the colonies, or syrup that is maybe a bit off, either due to manufacturing problems or sort of mismanagement in the way we handle and store our syrup. I first got interested in syrup back when some beekeepers in Manitoba, Saskatchewan, and the northwestern US purchased some off-spec corn syrup, got it for a really good price. They were told there's really nothing wrong with this except the sugar content is a little bit higher than normal, and it's probably going to be better for your bees. And so they all jumped on it, and they were all falling over each other to buy this stuff because it was cheap, and fed it to their bees. And then through some diligent work by then provincial apiarist Don Dixon and Riel Lafreniere and myself, we were able to figure out that it was actually the corn syrup that was causing their problem, and that one of the key factors in this corn syrup was the acidity of the syrup. Oops, not sure what happened there, but so this is just a picture of a cage study we did with corn syrup. These are healthy bees on the right. You can see the bees up at the top of the cage. They're fed, I think in this case, sucrose syrup. The ones on the left here were fed the off-spec corn syrup, and these are the bees down at the bottom. And you can also notice the gooey, sticky mess that's all over these hives, similar to what the beekeepers were reporting in their actual colonies. Now, if you're buying sugar, it can come from a variety of different sources, and I'm not going to get into the details of this because I was told to try and keep it down to about 40 minutes. So, but you can get it from sugar cane, sugar beet. These would both be sucrose syrups or corn syrup, which normally would get converted into a high fructose corn syrup. As long as they're high quality, any of those are okay. You want to stay away from things like unrefined cane sugar, though, because it's got a lot of particulates and things in it that cause problems. And in the old days, they used to produce acid hydrolyzed invert syrup. They don't really sell that extensively now. The stuff that they do sell is called medium invert, and it's usually okay to kind of use, but I think if you're using anything, be careful that you know what it is and make sure that it's of high quality. If you take sugars, sucrose breaks down into glucose and fructose, and the sugars then go on and continue to degrade into other components which are toxic. One of the main ones is this one called HMF, or hydroxy methylfurfural, and if you're looking at a spec sheet and you're seeing something in the range of 100 to 250 parts per million, that's kind of the range where there's documented scientific evidence that it causes harm in terms of the longevity of bees. But in addition to HMF, it further breaks down into other products, which research scientist Bailey has shown are also toxic by themselves. These include formic acid, which we use as a mite treatment, lavulonic acid and acetic acid, as well as some other compounds. So HMF can be there and then degrade further and kind of disappear. It doesn't mean the problem has disappeared. It means it's converted into something else maybe equally as bad. So HMF isn't necessarily a good indicator. In fact, these high fructose corn syrups that were quite deadly had reasonable levels of HMF. This graph just shows the HMF level for two off-spec syrups. One's 24.4, that should be in the safe range, but it caused one of the greatest levels of mortality. This one was 113 in terms of the ppm. That's an area where we think, okay, that one's borderline, might be a problem and cause problems. Some of the on-specs that were okay, though, overlap those numbers. So 15.8 and 28.2 both showed no kind of mortality, so those were safe. And then sucrose showed the highest levels of bee survival with, basically no HMF in the sucrose syrup because we just mixed it up fresh in these studies. So essentially, HMF doesn't seem to be a good predictor, and we did a lot of work trying to figure out what it was. We looked at pesticides, we looked at the types of sugars, all kinds of things. But we did eventually find out that there was a really good correlation between the pH of the syrup and colony mortality with syrups that were low in pH, so very acidic, causing high levels of mortality. And we did some studies to kind of look at this. I'm going to give you the Coles Notes version here, but essentially if you measure something called the titratable acidity, that can tell you how much buffering capacity is in that syrup, and if it overcomes the bee's natural buffering capacity in its gut, those bees end up getting dysentery, and then they ultimately often die over winter. You can get this tested by the KRTP here, but these are some studies we did with different levels of titratable acidity in a controlled lab study, and once you get up into the titratable acidity level of 5, which is 5 mils of 0.05 normal sodium hydroxide, to take it to pH 6, I think, 6.3, something like that. That is your kind of level where you start to see significant mortality in those bees. These intermediate levels are usually similar to what we might find in a high fructose corn syrup. And when you have syrups that are degrading or partly degrading, what we find is that bees that are in spring, when they can go out and they can fly, they can collect pollen, they can defecate, they can deal with that acidity quite more effectively than bees that are in winter. This graph just shows sucrose syrup that was 67%. That's blue is 1-year-old syrup, red is 2-year-old syrup, and green is fresh syrup. And you can see that there's some mortality in 1- and 2-year-old syrup when it's fed to spring bees, but it's much, much worse when fed to bees in winter. And that sort of trend seems to hold for almost all kinds of syrup. If you look at dilute syrup, that's 1 part sugar to 1 part water, the results are more dramatic. This is with a 6-month syrup and fresh syrup. The 6-month syrup fed in spring is pretty much okay, but if you feed that 6-month-old dilute syrup in winter, it's very degraded and very harmful to wintering bees. So it's going to affect your wintering bee population, and those long-lived bees that you work so hard to produce are going to get whacked. This sort of came to a head again more recently when we received some reports of beekeepers that got some syrup that was kind of frothy. This is a kind of a one here. I don't know if the sound is going to play.
It's playing on.
But this is Merv Mallion kind of looking at his syrup, and it's kind of got a frothy thing, and he kind of weighed it, and it didn't seem to have the right weight, and he was trying to figure out what was going on. So we took some of that, and we did a couple of things. One of the things we did was we put a lid on these things and we measured the amount of carbon dioxide that was in the lid. So we just used a carbon dioxide meter, poked it through the lid, and you can see the levels of carbon dioxide on this meter. So this is the little probe going into the headspace above the syrup. 45% carbon dioxide, which is, that would kill you if you stuck your head in there and sniffed it. Here's another one, just for an example. And I'll show the meter in a second. 90, well, that's 9.7%. So that's not quite as bad, but still bad. So there's something going on in there, likely fermentation that's causing it. We measured the titratable acidity in those syrups, and they had very high levels of titratable acidity. We did a study with Derek Mickelson, who was the KRTP program lead at the time, and got some help from Ian Stepler, who provided us some bees from his wintering building. And we loaded up cages and we fed them a whole bunch of these different syrups that had been provided to us from beekeepers. And we then monitored them in these cages and we measured their mortality over time. So some of them looked nice and healthy there. This cage here, quite a few dead bees already. And each day we would go in and count the number of dead bees, refresh the syrup, etc. And there was a pretty good relationship between the acidity level and survival, where as you got higher in terms of the acidity level, you got lower in terms of the survival of the bees. The workers also, interestingly enough, consumed more syrup when it was more acidic, and they consumed more water. And there seemed to be a bit of an interaction going on with nosema and some of the other pathogens. So just to give you one graph, the low varroa nosema, no nosema, low virus treatment, whether you fed the acid syrup, which was 2.6, or control, there was no significant difference. But if you put that under stress of a few pathogens, so moderate varroa, low nosema, and moderate virus, you started to see very significant differences in the survival of those bees. So if you had that syrup and you fed it, and your bees were super healthy, they'd probably tolerate it. They probably wouldn't have been affected. They'd probably come through the winter alive. But if you had that syrup, it's an additional stress on top of 2 or 3 other stresses, then it caused significant mortality. And those long-lived bees are going to have a shorter lifespan and possibly not make it through the winter. This study was a lab study. We had a lot of help, but we wanted to try and verify it on some real colonies. So we, in conjunction with Matthew, with the KRTP, set up an experiment. We had a producer that had quite a large volume of really bad syrup, and we were able to get some other bad syrups from a few other producers to test. And we tested those against high quality sucrose that was fresh. And we tried to get everything as good as as good as we could get it at the beginning of the experiment. And so we treated with 4 applications of formic boron treatment, and then did a post-treatment oxalic acid vapor treatment to try and equalize the varroa as much as we could. We weren't perfect at doing that. Some of the colonies that we got into this experiment had fairly high levels of varroa at the beginning, and our treatments didn't do a perfect job of knocking them back at the beginning. I think we got a pretty good knockdown by the time we hit the end of the experiment. So we essentially set up the colonies and we tried to equalize them in relation to their food stores, in relation to their colony weight, in relation to their colony size, so that the syrups that we were feeding would be kind of treated on an equal basis. And we measured the mite levels, and you can see that some of these colonies had quite high mite levels, getting around 20% mites in here at the beginning of the experiment. And as I say, we tried to knock those all down with formic acid. The mites did have a bit of an influence on our results, as I'll show you in a second. We transferred food between colonies. We weighed them all. We weighed frames and did a lot of juggling and balancing weighed colonies before, we adjusted them, weighed them after, try to make them as close to the same as possible. And then we fed the syrup in just gravity feeder pails with randomly assigned throughout the apiary. One of the things that we noticed is that the bees took some of these syrups much faster than others. This one that had a titratable acidity of about 6 really got sucked down quickly. This graph just shows you the date at which the pails were judged to be totally empty, and they really sucked that down quickly. The control syrups and the ones with lower acidity, they tended to often take much longer to fully drain. So just because something is being taken down quickly, it doesn't mean it's necessarily good for the bees. And after we fed them, we did the same types of population assessments. We weighed the colonies after feeding, measured their populations. And this shows the mean change in weight of the colony over time, going from the 28th of September when we started the experiment to the 26th of October. And if you look at the relative change in weight, as bees eat the syrup, they lose weight. That's expected. So the controls lost weight, but the 5.9 syrup, the one they took down really, really quickly, lost weight at a much greater rate than the controls, statistically significantly greater. These other ones also lost weight, but at a similar level to the controls, and there weren't as many replicates in those syrups. We didn't have as many pails for those, so part of that may have just been not enough sample size. We measured populations as well. Here's Matthew and I tipping up hives and scoring them. And if you look at the mean fall cluster size, these colonies all looked really great. At the beginning of the experiment, they all had a cluster size in the range of about 8.5 to 9 frames of bees. We had them in single brood chamber colonies. And we saw that if you looked at the change in cluster size, there was a slight reduction as temperatures got cooler and some of the older bees died off. Relative to the control, which is this bar here, the 5.9 treatment and this one, which was about 6.1 to 7.8, lost more bees relative to the control. And these two on the end, again, not statistically significant, but they're maybe partly due to sample size. We did, by the time we hit the end of the oxalic acid application, got pretty good mite control, so a lot of our treatments were equivalent at that point. But some of this initial variation in varroa mites, which I talked about earlier in the talk, impacted the experiment. If you look at the control, you can see that even with a 20% mite infestation, the control still has a really high cluster size going into the fall, whereas those treated syrups that had, not treated, they were badly treated, I guess. Syrups that had high levels of acidity, titratable acidity, had much lower cluster sizes when there were high mite loads. But when the mite loads were quite low, they were about equivalent at that point. So there is a bit of an interaction going on between varroa and syrup, as we might expect from previous data. When we looked at these midwinter, we did see some signs of serious dysentery, as you might expect with acidic syrup. This is one of the colonies, P7, taken in the fall of 2023. This was taken in our wintering building, and all this blackness and goop up here that you can see is dysentery, likely associated with the acidic syrup. So we are still processing data from this experiment. Amanda and the KRTP people, Matthew, we've got a lot of Matthews. There's a Matthew that works in my lab. There's Matthew that's KRTP. There's a couple of KRT people right there that helped in the experiment. And all these people in this slide here that really helped out. But we're still processing the data in terms of population scores, brood area and stuff in the spring. So once we get that all done and wrapped up, we'll probably have some more data to report to you. So I'm not sure, I'm pretty sure it took you 10 minutes before you started. So I think I'm going to declare myself as on time. Yeah. Any questions?
I got a question.
Yep.
You said don't disturb the bees in September because the winter bees are starting and stuff like that. What would you do or not do that would affect it?
Yeah.
I know you're talking about treatment. The formic is reducing the brood and all that kind of stuff. Okay, that's one. What else?
Yeah, I mean, try and get your treatments a really good mite control in the spring is probably the best advice. But you know, if that doesn't happen and you get into fall and you're in a situation like I am in with these 2 colonies at the lake where I've got really high varroa, do I put Apivar in there and maybe take a chance? Some of the stuff that we have done seems to suggest that you're probably best to delay the Apivar, maybe hit them with some formic right away and do a late Apivar, or I'm not convinced the early oxalic late Apivar is going to be effective, but if I was going to do it, I might go with Apistan if I thought I had no resistant mites, and then that would probably provide your best bet, but I'd be hesitant to, if I had really high mite levels right now, to put a Apivar in right away. I'd probably wait till closer to the end of September and then throw the strips in, which is counterintuitive, but I think that might be the best advice with really high levels of mites. Like if you're in the 20% range right now, you know, you're kind of, but if you're 1 or 2 or 3%, put your Apivar in. Yeah. Yep.
Was the pH of the water when you made the syrups, pH of the water taken into consideration for these?
Yeah, when we do the titratable acidity, you basically take a syrup and you dilute it with water. So we use millipore water and we measure the initial pH of that water. But the syrups themselves are purchased from the manufacturer usually, a supplier like the co-op or a different supplier, or sometimes they come directly from the Tabor plant, or you know, maybe it's a beekeeper who stored it in their shed and it's been there over the summer and got really hot and they're concerned about it. So in that case, we don't really know what the initial pH of the water is, but to tell you the truth, the initial pH of the water doesn't make that big a difference. You know, it's kind of like 1 drop of the sodium hydroxide and if there's no buffering capacity in the syrup, that'll just change the pH right away. But if it's got a problem with buffering from too much acidity, then you have to put like 5 mils in rather than a drop. So that initial pH of the water almost doesn't factor in. Yep.
Two questions. The first question is more of an answer.
Mm-hmm.
Like the water pH in Manitoba is almost always over 7. You would.
Yeah, not in our lab. The stuff that comes out of our tap is closer to 6, 6.5 often.
Is that because it's fluorinated?
Maybe, yeah, I don't know. But you know, we have tested water from different areas. Like there were some producers came from areas where they had a high sodium well, and we've tested that, but haven't seen any negative effects from that. But you know, we haven't tested. We sometimes get water that's over 7, but from the stuff that comes out of our tap in the lab is almost always under 7.
Yeah, most well water or stuff that's coming out of lagoons tends to be over 7.
Right.
Quite a bit over 7. The other question, I have some pails of sugar syrup from last year. Would you recommend I just throw it out?
I would
Feed
recommend,
it?
yeah, I mean, there's 2 answers to that. One is don't feed it now, feed it next spring. And if you're going to feed it next spring, the old saying, dilution is the solution to pollution. kicks in, and you could dilute that down with some good syrup. There's probably, I'd also take a refractometer refractometer reading on it, and if it's got still a high concentration of sucrose, then it'd probably be okay to feed diluted as a spring feed.
Some of the feeding stimulants that are being sold to put in sugar to get bees to take them up tend to be on the acid side.
Yeah, there's things like lemongrass oil we've tested, and thymol. We've tested. Some people use honeybee healthy and things like that. But generally speaking, it's not a good idea to use acidic products and add them to your syrup, because it'll if there's heat plus acid, it'll degrade the syrup more quickly, and you'll get also the formation of HMF. In fact, the original studies that were done by Bailey were done when the beekeepers, he discovered the beekeepers were making queen candy using tartaric acid, and they were having all kinds of problems with the queens dying. And that's how they discovered HMF. That's how they discovered all these breakdown products. It's because the beekeepers were using this recipe to make queen candy, where they mixed tartaric acid in with the crushed sugar and try and make a nice, soft, pliable queen candy, and that was what was causing the toxicity. It was a result of the HMF buildup and other acids that built up in that queen candy. So yeah, be careful with a lot of these. I think the KRTP, Matthew and I have talked about, I don't know if Matthew's here, he said he might be here, yeah, talked about maybe testing some of those. We didn't get around to doing it this summer, but I think it's on Matthew's list.
I have one more question for you.
Yep.
You talk about syrup, but what about honey? I have frozen honey, and I have also honey that's been left out in the non-existing hive, which means there's no bees in there, all summer. Can I use that to feed my bees in the fall? Or is it gonna be like very toxic or?
I'd probably use the same advice and say to feed it back the next spring. Honey can be as bad as bad syrup. I know, for example, Bailey tested 8-year-old honey, and it was as bad as some of the most toxic syrups. So the same types of things can happen within honey that happen within other products. I think honey does have some advantages that I kind of have I tried to test this and I failed, but I still like the idea. I said there's natural pollens and things in honey that I think might, sort of resupply the buffering systems within the bees. There's probably two or three maybe buffering systems within the bees that use various compounds. Phosphate is one of them. And that has to be regenerated for the bees to maintain their power to buffer these syrups. And the natural components in honey that contain pollen might provide some of those nutrients that allow that. But I tried feeding pollen and feeding bad syrup, and I was unable to mitigate the effect. So that's one of my great ideas that kind of blew apart. I still like it though.
So frozen honey is okay, but the one that's been out all summer is not.
Yeah, it depends on what kind of honey too it is, I guess. Like if it's canola honey, don't feed it. If it's
Dead out, like from winter, it didn't survive.
how long a dead out? Because we did studies.
Last fall, right?
Last fall would be okay probably, but do be careful about feeding honey and combs from dead outs, because we have tested that as well, and it's quite detrimental to the buildup of colonies in spring. So the viruses are retained in the comb and last for quite a while on the comb and can reinfect colonies. Once you get beyond about 3 months, those virus levels start to drop. And when we put the comb back into colonies, if you put it in May, then the virus levels have returned to sort of normal by the end of summer. So it can take quite a while for those viruses to sort of equalize to the point where they're no longer causing any kind of impacts.
I have canola fairly close to me, but also the floodway less than about half a mile away from me. How can I tell that whether the honey honey that's being stored in the brood boxes right now? Because there seems to be like a frame or two in each box, whether it would be canola honey.
Yeah, I don't know. Good question. I mean, they could send it in for honey analysis, but they probably charge an arm and a leg for that. You know, I think if you're feeding, if it's 1 or 2 frames and you're feeding now, the bees are going to be recycling that with the syrup and consuming some of the old stuff and remixing it. You're probably going to be okay. But if it was like plugged all the way through, then it might be more of an issue. But I think I wouldn't worry too much about it if it's just 1 or 2 frames myself. The bees will move honey around too. Steve Purnell did a study where he's trying to figure out, about drug movement within colonies, and so he put some food dye in his colonies. It was kind of like a blue-green food dye, and the bees moved it all over the hive, and so the honey came out this like green-blue color, and so he saved it for years, and they couldn't get rid of it, so he finally put it in jars and marketed it as Northern Lights honey.
So why did the bees do that?
What's that?
Why did the bees do that?
Why do they do it? They're bored. I don't. I really don't know. They do move stuff around though within the brood nest for sure.
Just a little question too. I guess. Are you suggesting not to use a feed stimulant in the fall, like a Hive Alive or any of those things with lemongrass in it?
No, I didn't say that. I mean, a lot of people use it. It's not really registered. So it's kind of one of these gray areas in terms of regulations and things like that. But certainly, one of the producers that had bad syrup had used lemongrass oil, and we tested lemongrass oil. One of the producers that had bad syrup had used thymol. We tested that in combination, and those weren't affecting the results. So in those 2 instances, they didn't seem to be increasing the acidity, put it that way. So, but I haven't tested every product that's out there. So
let's collectively thank Dr. Currie.
thank you.
So just a little something. We had previously, at our annual meeting in January, we put the motion forward and voted and accepted to offer a lifetime membership to the Red River Apiary Association for you. So we've done that, and we just have a little official certificate that we've
Thank you very
made
much.
up for you.
Thank you.
Thank you.
Thank you.
Thank you very much.